Now let's explore how we can observe and measure the nanoscale materials and devices. These methods are critical for the realization of nanomaterials and nanostructures into useful nanointermediates. By measuring the physical and chemical properties precisely, we can prepare the nanointermediates in the designated manner, and by observing the physical and chemical phenomena, we can control and revise the devices as well as materials. One of the most challenging points of the nanoscale is that it is impossible to use optical signals for the measurement and observation. This is due mainly to a fact that visible light, which spanning from 400 to 700 nanometers, has too long wavelength to be applied to sub-100 nanometers nanoscale world. Due to optical diffraction, there exists Abbe's resolution limit, which indicates the separable resolution d is linearly proportional to the wavelength lambda. For typical visible light, this resolution has a minimum limit of 250 nanometers. This means that we can't see or measure the nanoscale materials or devices by just using optical apparatus such as optical microscope. As shown in this comparison on the right, Abbe's limit could not reach sub-100 nanometers, and therefore, it is not relevant for the optical microscope to observe virus, protein, quantum dots, nanotubes, and other small molecules. The Abbe's diffraction limit is given by the point dispersion function, which is typically Airy function as shown in the lower left illustration. As shown in the lower right illustration, two close features will make overlapped portion of the diffracted light, and the more the overlap, the harder the discrimination of two neighboring features. There are various conventional resolution limits for optical microscope. First, in the Rayleigh convention, the first minimum of one Airy profile overlaps the maximum of the second Airy profile, with the sum of the two profiles showing a distinct dip. Second, in the Abbe limit, a small dip is still discernible between the two maxima. Third, in the Sparrow criterion, the sum of the two Airy patterns produces a flat intensity profile. Therefore, the two maxima are not discernible. Basically, the spatial resolution of the imaging is a function wavelength. As shown in the right figure, when we have sufficiently short wavelength light source, the resolution is not the problem. However, when we have somewhat long wavelength, the images are not fully separated. Therefore, it is reasonable to scale down the wavelength of the light source for the exploration of nanoscale world. Below the visible spectrum, we can use shorter wavelength electromagnetic waves such as ultraviolet, X-ray, gamma ray. Instead of the conventional electromagnetic wave source, we can use electrons as wave source. According to quantum mechanics, electrons also have wave-particle duality like photons. Using de Broglie wavelength calculation, it is possible to estimate the wavelength of electrons, which is about 1 to 10 nanometers. Okay. Let's learn more about the electrons as short wavelength wave source. In scanning electron microscope, electrons work as wave source. First, an electron beam is scanned on the sample. When a focused electron beam reaches the sample, it interacts with the sample's atoms and produces different signals. During the interaction, secondary electrons originate from a few nm from the surface. Detection of secondary electrons emitted by the atoms on the surface and a few nanometers below the surface. Actually, scanning electron microscope depends on the electrons and their interaction. It requires a conductive sample. If sample is not conductive, you need to sputter a conductive metal on the surface before imaging. The sample stage can be tilted. The brightness of the image depends on the number of electron detected. As shown in the right schematic figure, the image intensity is proportional to the secondary electrons escaping from the surface of the sample. The escaping rate of the electrons is proportional to the area under the exposure of the electron beam. Typically, the exposure area is greater for the tilted or sharper than flat area. Therefore, typically, edges appear brighter than flat areas.
문 닫아, 베란다 문 닫아, 태호가.
An electron beam is transmitted through a very thin sample and interacts with the sample. A resulting image is formed on a fluorescent screen, where the intensity reflects the number of electrons reaching the screen. The most commonly used imaging mode is the bright field mode, where thicker regions of the sample and regions with a higher atomic number will appear darker. A small voltage difference is applied between the sample and the tip so that electrons can tunnel through the thin barrier between the tip and the sample. For example, the barrier for typical devices is vacuum or air. The resulting tunneling current depends on the tip sample distance and on the local density of states. During scanning, if one adjusts the height of the tip to maintain a constant current, the tip will follow a constant density of state. Tunneling is highly sensitive to changes of the barrier width. The main advantage of tunneling electron microscope is its high resolution. For example, it has lateral resolution of 0.1 nanometers, while depth resolution is 0.01 nanometers. However, this advantage requires very sharp tips such that one atom at the end. In addition, the lifetime of the tips is very short. It can't be reused after 2 or 3 times. Along with electron microscope, it is possible to use near-field generated by nanoscale tip. The microscope which use the nanoscale tip for nanoscale imaging is scanning probe microscope. It has a great advantage different from optical or electron microscope, which is no diffraction limit. This is mainly due to the near-field generation around the probe. The first scanning probe microscope was invented in 1981 by Gerd Binnig and Heinrich Rohrer at the IBM lab in Zurich. Since that time, a vast family of scanning probe microscopes has been spawned, a few of which are represented in this family tree. Despite the huge number of types of scanning probe microscope and modes in which they can be operated, the underlying operation is the same for them all. Each different type of scanning probe microscope is characterized by the nature of the local probe and its interaction with the sample surface. The first scanning probe microscope is Scanning Tunneling Microscope (STM). As the name indicates, STM utilizes quantum mechanical properties such as tunneling of electrons. As many of you had already learned in the quantum mechanics course, the tunneling or the quantum tunneling is the quantum mechanical phenomenon where a subatomic particle passes through a potential barrier. Quantum tunneling is not predicted by the laws of classical mechanics where surmounting a potential barrier requires enough potential energy. Fundamental quantum mechanical concepts are central to this phenomenon, which makes quantum tunneling one of the novel implications of quantum mechanics. Quantum tunneling is projected to create physical limits to the size of the transistors used in microprocessors, due to electrons being able to tunnel past them if the transistors are too small. STM operates by taking advantage of the relationship between quantum tunneling with distance. As shown in the left figure, when the tip of the STM's needle is brought very close to a conduction surface that has a voltage bias, by measuring the current of electrons that are tunneling between the needle and the surface, the distance between the needle and the surface can be measured. By using piezoelectric rods that change in size when voltage is applied over them, the height of the tip can be adjusted to keep the tunneling current constant. The time-varying voltages that are applied to these rods can be recorded and used to image the surface of the conductor. STMs are accurate to 0.001 nanometers, or about 1% of atomic diameter. Therefore, it is possible to image the atomistic features such as the image of gold surface shown in the middle, surface of crystalline silicon as shown in the upper right, and some xenon atoms controlled by the STM as shown in the lower right images. Along with the atomistic imaging apparatus, STM can work as a top-down patterning technique. Due to its controllability of a single molecules with atomistic tip feature, STM can move or remove some of the molecules adsorbed on the surface as shown in the left figure. Through the tip, it is also possible to guide electrons or molecules to the underlying surface or self-assembled monolayer. Using electrons, it is also possible to oxidize or etch underlying monolayer of molecules as shown in the right figure. These techniques precede the dip pen lithography or AFM-based top-down patterning. Atomic force microscope is one of the well-known and heavily used scanning probe microscope. It had also been developed in the early 1980s at IBM Zurich. Atomic force microscope gives access to the topography of the surface with typical resolution of 30 nanometer in plane direction and 0.1 nanometers in depth direction. The resolutions depend on the tip shape. There are many ways to image the surface. The simplest one is contact mode. In this mode, the tip on a cantilever in contact with the surface with a given deflection of delta Z sub 0 which corresponds to a force F sub 0. The sample is placed on top of a scanner that can move in XYZ. During XY scanning of the sample, when the tip scans a bump of height delta Z on the surface, the force exerted on the tip is F is equal to F sub 0 plus K times delta Z. In the course of the atomic force measurement, the photodiode measures the deflection of the tip. As shown in the lower right schematic figure, a feedback loop adjusts the sample height to maintain a constant tip deflection to delta z sub 0, which corresponds to a force F sub 0, which is a constant force on the tip. The displacement of the scanner in z as a function of x and y gives the surface topography. Atomic force microscope can also be used for top-down lithography method. Compared to E-beam lithography, AFM-based lithography has larger spatial resolution. However, it is advantageous in several aspects. First of all, the tip can be used for electric conductor, which can apply and focus electrons on specific areas to initiate oxidation as shown in the left figure. Second, AFM can provide tip-induced chemical modification on the specific area of the surfaces. As shown in the middle figure, conductive AFM tip can apply electron beams on top of the self-assembled monolayers. As shown in the right figure, this approach can be applied for the fabrication of layer-by-layer nanostructures. In addition, if we employ multi-tip array, AFM-based lithography can be applied for large area with fast patterning process. Similar to the AFM-based lithography, there exists another tip-based patterning technique. This technique is developed by American chemist Professor Chad Merkin at Northwestern University in Chicago in around later 1990s. This technique uses AFM tip, which is covered by some chemical molecules. These molecules are transferred from the tip to the surface of designated substrate. By moving the tip with nanometer position control, it is possible to write a variety of materials including proteins, DNAs, nanoparticles, nanowires, or quantum dots on the substrate as shown in the right figure.